meaning of integrals. What does it mean, right? We saw this when we say integral from a to b of velocity function times dt, right? What's the meaning of this? This is what we call, well, antiderivative evaluated b minus antiderivative evaluated a, isn't it? And this is what we call delta x, displacement a. Okay, so there's that. What about this integral then? A to b of absolute value of velocity. If you evaluate this, what does that mean? Oh, come on, people. You had a test on this. This means distance. Okay, these two are biggies. Now, there's more really, and that's this third example. When you apply a force on an object in order to move it, so if you have force function, and this is a function of x, and this force may or may not be constant, and then the way it's written right now is not constant from point A to point B. This gives you work. Okay. Now, so integrals physically have many different meanings, and this is not all of it, but these are the three main things that is used in physics. Okay. Now, let's take an example. Say, you know that the garage door has spring, right? And then it opens and closes, and they have springs have something called the spring constant. So as think about the spring, and then no real springs behave this way, but it's called the ideal spring. Mostly, ideally, if you stretch the spring, then it gets harder and harder and harder, right? So if we graph that thing, say we have, this is a graph of x, let's say in meters, and then amount of force it requires, this is in newtons, to stretch this thingy, right? Then it's going to look like this. You know what I'm saying? So more you stretch, harder it gets. So you have to apply more and more and more force to pull it. You know what I'm saying? Okay, so this function can be given by f of x. It's a function of x, not function of time in this case, because this velocity was function of time, but this is function of x. Because if you think about it, it depends on the amount of stretch from equilibrium point, and then also compression as well. Okay, this is equal to, okay, this is force of the spring. This is typically what your physics, so I'm going to be careful and then use a subscript, negative kx. What that means is if you stretch it, spring wants to pull it back. So it's the opposite direction. The force is the opposite direction of your movement, your displacement. You get it? If you compress it, spring will fight it and then wants to stretch now. But this is F external, this is U. That'll be just Kx, isn't it? Because you want to stretch it that way. You know what I'm saying? So these two are opposite and they are balancing each other out. Initially this needs to be slightly greater than that, but after that you can pretty much keep it as the same amount of force so that you stretch it at a constant speed. All good? Okay. Now, then the other thing that physics teachers teach you is work is equal to displacement, eh? Well, let's just put delta. Work is equal to force times displacement. That kind of makes sense. Say there's a shopping cart full of groceries, and you're supposed to push it from here to the cash register, or in the parking lot from as you exit the grocery store, and you have to push it to the cart. You know what I'm saying? So pretty more or less it's going to be the constant force that you're pushing this cart with. So if it's heavier, then it requires more force, so you're doing more work. At the same time, if it's farther, if your car is far away, then you have to push it farther this distance. So that is, you're doing more work. You know what I'm saying? So you see why it depends on both of them, force, the amount of force that you have to push this thing with, and then also amount of displacement, right? So that's how they define work. If this is twice as heavy, you do double amount of work. If this is twice as far, you also do double amount of work. So if it's twice heavy and twice as far, then you have to do quadruple amount of work. Make sense? Problem right here is that is only true if this is constant force. You know what I'm saying? And as you can see in the case of the spring, it's not so constant. Then what do we do? Ideas? What we can do is rectangle approximation. So, and we have done this before. Say we fit these rectangles here. So approximately this is constant, right? We have done this before, and we are going to take the limit as this thing gets infinitely thin anyway. So this amount is your force right here. External. And then this is delta x. You get it? And all we have to do is add these rectangles up from 0 to some distance. You know what I'm saying? And suppose we want to go from 0 to here, and that we'll call x. X not x, whatever. Let's just be a little sloppy. Good. So amount of work now is then really f(x) dx from, in this case, 0 to x. You get it? Okay, now there's only one problem with this. And one problem is, you see x here, and you see x here. Oh, if you ever do that in a math class, your anal professors and also these AP graders, for all anal math teachers, they will have a heart attack. You cannot have x here and then plug in x for x. Like, wow. No. They will deduct mass amount of point if you do such a thing. You know what I'm saying? However, if you go take the physics at the same time, engineering, they all do this. I'm quite used to it. But for now, let's just say this is known as a dummy variable. Let's get rid of these things. And then we'll put s then. How about that? So that when we substitute, we don't have a problem. You know what I'm saying? Because s will disappear. Sometimes people put t, but in context of physics, t also represents time, so we don't want to do it. So it's just like use any variable other than x. You know what I'm saying? Okay, then we are ready to evaluate this. So if we evaluate this, then, well, we have to figure out this force first. Oh, well, actually, I'm going to use this thing, kx, right? So we have 0 to x, ks ds. You get it? You see why this has to become s now instead of x? You guys are smart enough to see that. It's just a variable. And then that, of course, is ks squared, and therefore 1/2. And from 0 to x, right? You with me? Now, and then we substitute, so we have 1/2 kx squared. I mean, I could have easily used the x in here and then s up there, but this is what your physics teacher will teach you, so I wanted to make it consistent, okay? This is also, this is the amount of work required to stretch or compress the spring, ideal spring, by distance x from the equilibrium position. And also, this is the potential energy, therefore, because energy is conserved, required to compress or stretch the spring. Good. Now we are ready to do this problem. So this first piece of information, 200 Newton will stretch the garage door spring 0.8 meters. This is there to figure out the amount of, well, the spring constant K. Okay, so I'm gonna do this problem now. So F is equal to Kx, and let's not get so hung up on this negative sign. It depends on which force it is, right? But let's say you are supposed to, this is external force. You are stretching this, okay? Now, therefore, that tells you K is equal to F over X now, right? Say yes. And that is 200 Newton divided by 0.8. Good. And somebody tell me what that is. Okay, thanks a lot, useless kids. 250 Newton per meter. That is the unit. So most constants in physics has unit, right? Because that's also converts one quantity to another quantity. Very good. Now we figured out what that is. That's what K is. Later we're going to use it. Now, then we have to figure out, well, 300 Newton force. So we are now exerting 300 Newton. And then we have to figure out how far that spring will stretch. So now what we have to do is X here is equal to F over K now, isn't it? And then we are using 300 Newton here over, we have 250 Newton per meters. Question so far? Are we good? Okay then. That is equal to, can somebody tell me how to simplify this fraction before I write it? This is calculus BC, you guys are scaring me. Okay, 1.2, I'll take 1.2, whatever, okay, right. 1.2 it is, good. Okay, are you with me? And then work that is required. We can integrate it, but why don't we recycle our work that we already have done here, okay? So work is 1/2 kx squared, you get it? So that is equal to 1/2 times 250 Newton per meters and times, and our x is 6/5. Does anybody care to do this one?
But don't we have this on?
Oh my god! Oh my god! Of course we do. Nice catch. Okay, that is too much. You may use a calculator now, because that is definitely too much. It will give you 180 joules. Okay? How about that? You kind of get the sense of integral and how to use them. Depending on the context, integral can take many meanings. And this is not all of it. I mean, there's a lot more. Integral is whenever you have to multiply two quantity, but the quantity that you're multiplying varies. I mean, this could be any function, right? And of course, integral does give us area under the curve. So whenever you have a graph, and then whatever the quantity you're calculating can be represented by the area under the graph, and then you integrate.